Suppose we have a car traveling around a flat curve. We want to know the centripetal force that's being exerted on it as it negotiates that curve. And then once we know that force that it has to be exerted on it, we can find the minimum coefficient of friction that we need between the tires and the road in order to take that corner at that speed. There are some significant modeling assumptions that go into this that aren't really what's going on with the car. For example, the car has suspension stuff that try and make your life easier with a little bit of mechanical advantage as you go around turns. We're just ignoring all of that. We're just focusing on what's happening between this wheel and the ground and not worrying about some of the more complicated things that people have implemented to try and overcome this physics. All right, we're traveling around a turn. This is a back view of a car. Let's look at a top view as we go around this turn. So we've got a turn. This is a circular turn. And we have a car going around the turn here, right? What that means is we have to have some centripetal force, Fc, that's acting towards the center of this turn as we turn around here. So this top view will help us understand like the centripetal part, right? That's the curved path. We can now look at what's happening here, and we already have a free body diagram drawn for us. We've got our car that has the normal force responding to the weight acting down, and then it's the frictional force on the tires is the only thing that's keeping us going towards the center of this circle. We can apply Newton's second law. Sums of the forces are equal to mass times acceleration. And consider the centripetal component of this. So in this centripetal direction, like this way, the only force that's acting in that direction is my centripetal force, and that has to equal mass times acceleration in the centripetal direction. I can write that as Fc is equal to mass times my centripetal acceleration of v squared over r. We know from the problem statement what some of these things are. I maybe should have labeled them explicitly, but let's just go ahead and plug them in right now. We've got 900 kilograms worth of car that's turning, and it's traveling 25 meters per second. So that gets squared around a 500 meter radius turn. When we evaluate this, we end up with centripetal force that has to be exerted to make this happen of 1,125 newtons. Now for part B, assuming an unbanked curve, we want to find now the minimum coefficient of friction between the tires and the road. And we say static friction because the tires should not be slipping with respect to the road here as we're making this turn. As they start slipping, that's where we start skidding out. Or you're watching a Gymkhana video and you're doing fancy drifting, but we're not worrying about that. We're trying normal handling. So for part B, let's consider that normal force and sum our forces in the y direction. So this is our up and down has to equal mass times acceleration in the y. And we're not coming up or down off the surface here, so that's 0. We can now say the normal force is acting up, the weight is acting down. That sums to 0, which means that we can write that my normal force has to equal the weight, which is mg, which is 900 kilograms times g of 9.8 meters per second squared. So we have a normal force of 8,820 newtons. With that normal force now, we can go back to that centripetal acceleration and say that this centripetal force is coming directly from static friction. So the maximum static friction we could ever have is mu Sn. We can now solve for mu s, the thing that we want to find, in terms of our static friction and our normal force. We can plug in the static friction has to be 1,125 newtons in order to make this turn. And the normal force is 8,820 newtons based on the weight of the car. When you divide those, you get a minimum static frictional force between the tires and the pavement of 0.13. So you need at least that much for this to work.